Welcome to the Deep Sleep Science Channel. Tonight, we gently wander through a world filled with quiet, wonders, strange, beautiful, and calming truths that exist all around us, often unnoticed. As you settle in, let your mind slowly drift across distant planets, deep oceans, silent deserts, and even the hidden systems within your own body. Before sleep begins to take you, you're warmly invited to like the video, subscribe to the channel, or leave a soft comment below. And now, with everything slowing down, let's begin this peaceful journey through some of the most fascinating and soothing facts in science. A day on Venus lasts longer than a Venus year, which sounds impossible at first, but it happens because Venus turns on its axis extremely slowly. The planet takes about 243 Earth days to complete one full rotation, while it takes only about 225 Earth days to travel once around the Sun. In other words, Venus finishes a whole trip around the Sun before it fully turns around one time. It is a wonderful reminder that words like day and year do not always mean what they mean on Earth. Sunrise to sunset on Venus takes about 117 Earth days, so the Sun would move across the sky there with astonishing slowness. On Earth, daylight changes hour by hour, but on Venus, the motion of the Sun would feel almost frozen compared with our familiar pace. If someone could safely stand on its surface, the sky would change so gradually that one single stretch of daylight would last for months. It gives Venus a strangely stretched sense of time. Venus also spins in the opposite direction from most planets in the solar system, which is why scientists call its rotation retrograde. On most planets, the Sun would appear to rise in what we would think of as the east and set in the west. But because Venus rotates differently, the pattern of day and night would be reversed compared with the usual planetary rhythm. It is one more way that Venus seems both familiar in size and completely alien in behavior. Venus is the hottest planet in the solar system, even hotter than Mercury, even though Mercury is closer to the Sun. The reason is Venus's extremely dense atmosphere, which traps heat with extraordinary efficiency through a runaway greenhouse effect. That blanket of gas holds warmth so well that the surface stays brutally hot almost everywhere. It is one of the clearest examples in the solar system of how atmosphere can matter more than distance. The surface of Venus is hot enough to melt lead. That fact helps show just how extreme conditions are there, because lead melts at a temperature far beyond anything found in ordinary life on Earth. Venus may look soft and bright through telescopes because of its pale clouds, but below those clouds is a world of crushing pressure and furnace-like heat. It is a planet that appears gentle from afar and violent up close. Titan, Saturn's largest moon, has lakes and seas made not of water, but of liquid methane and ethane. On Earth, those substances are gases under normal conditions, but Titan is so cold that they can exist as liquids on the surface. This gives Titan a familiar-looking landscape of shorelines, pools, and weather, but with completely different chemistry. It is one of the most Earth-like places in appearance, and one of the least Earth-like in substance. Saturn's moon Enceladus sprays jets of water vapor and ice into space from cracks near its south pole. These towering plumes erupt from the icy surface and send material outward into the darkness around Saturn. That alone is unusual, but what makes it even more exciting is that such eruptions suggest hidden internal activity under the frozen crust. Enceladus looks quiet from a distance, yet it is one of the most active small worlds ever discovered. The long fractures on Enceladus are nicknamed tiger stripes because they look like parallel claw marks across the ice. These striped cracks are not just marks on the surface. They are the places where the moon's icy shell opens enough for water vapor and icy particles to escape. The nickname gives them an almost animal-like character, but the science behind them reveals a moon with heat, motion, and possible liquid water below. Saturn is not the only planet with rings, but its ring system is the most complex and visually dramatic in the solar system. The rings are wide, bright, and beautifully layered, appearing almost like grooves in light from a distance. Yet they are not solid sheets. They are made of countless separate particles, orbiting together in an elegant and dynamic structure. Saturn's rings are one of the clearest examples of nature creating something that looks almost designed. Some Martian twilight clouds become iridescent, showing soft red and green colors after sunset. These clouds do not glow because they are producing light. Instead, their tiny particles scatter and bend sunlight in ways that create delicate shifting colors. It means that even on a cold, dusty world like Mars, there can be moments of surprising beauty in the sky. The idea of pastel-colored evening clouds above the Martian horizon feels both strange and peaceful. Mars can form high, faint clouds made partly of frozen carbon dioxide, which is dry ice. On Earth, clouds are made mostly of water droplets or ice crystals, so clouds of dry ice sound almost unreal. But Mars has a very different atmosphere, and under the right conditions, even carbon dioxide can freeze high above the ground. It is another reminder that the skies of other worlds can follow rules that feel almost unfamiliar enough to be dreamlike. The highest Martian twilight clouds observed by the Curiosity rover were about 60 to 80 kilometers above the surface. That is an enormous height for clouds, placing them far above where most clouds would form in Earth's lower atmosphere. Their great altitude helps explain why they can still catch sunlight after the ground below has entered darkness. On Mars, evening can linger high in the sky long after the surface has dimmed. Some of the most colorful clouds ever photographed on another planet were observed on Mars rather than on Earth. That is a surprising thought, because Mars is usually imagined as red, dusty, and almost colorless. Yet under the right conditions, its sky can display subtle, shifting tones that feel delicate and unexpected. Even a world known mainly for rust-colored deserts can sometimes offer a surprisingly gentle palette. Red sprites are giant flashes that can appear high above thunderstorms instead of below them. Most people imagine lightning traveling between cloud and ground or within clouds, but sprites happen far above the storm tops in the upper atmosphere. They can stretch upward in huge, glowing forms, linking ordinary weather to much higher regions of the sky. It makes thunderstorms seem even larger than they appear from the ground. Sprites are usually red, can resemble jellyfish or columns, and may reach up to about 60 miles above the cloud tops. Their shapes can seem almost alive, with delicate tendrils and branching forms that hang above the storm. Yet they are not living things at all. They are electrical events shaped by the atmosphere itself. Their great height and strange appearance help explain why people once described unusual skylights in mysterious terms. Blue jets shoot upward from thundercloud tops and can fan out like narrow cones in the upper atmosphere. Instead of reaching downward like ordinary lightning, they rise into the layers above the storm. Their color, shape, and direction make them look like something entirely different from the lightning most people know. They reveal that a thunderstorm is not just a cloud system, but part of a much taller electrical structure. Gigantic jets can extend even higher than blue jets, reaching toward the ionosphere. These are among the most dramatic upward electrical events known in Earth's atmosphere. A single storm can, under rare conditions, connect lower air to the very high electrically active layers above. It is remarkable to realize that familiar weather on the ground can sometimes reach into regions of the sky that feel almost space-like. Moonbows exist, which means moonlight can produce a rainbow under the right conditions. The process is the same basic one that creates a daylight rainbow, with light bending and separating in water droplets. The difference is that the light source is the moon, using reflected sunlight, so the effect is fainter and often more subtle. A rainbow at night sounds like fantasy, but it is a real and measurable event. A green flash is a real optical effect that can appear briefly near sunrise or sunset when the atmosphere bends light by color. For a very short moment, the upper edge of the sun can appear green. This does not happen because the sun itself changes color, but because Earth's atmosphere acts like a weak prism. It is one of those quiet, natural effects that seems magical only because it is so brief and easy to miss. Noctilucent clouds are so high that they shine after sunset, when lower clouds are already in darkness. They form near the edge of space, in an extremely thin part of the atmosphere far above normal weather. Because they sit so high, they can still catch sunlight long after evening has reached the ground. This allows them to glow softly in the twilight sky, while everything below them is already dark. Some auroras occur so high in Earth's atmosphere that they are linked to particles escaping into space. That means an aurora is not only a light display, but also part of a larger interaction between Earth and the space environment around it. The upper atmosphere can glow while also losing particles upward. So in a quiet curtain of light, there may also be motion, escape, and exchange happening far above us. Scientists have launched sounding rockets through unusual auroras to study how Earth's upper atmosphere can leak oxygen into space. These rockets briefly travel through specific regions to collect measurements directly inside the glowing conditions. It sounds extraordinary that scientists would send instruments through aurora light, but doing so helps them understand how Earth's atmosphere behaves at its outer edges. Even our planet is not fully sealed off from space. The sun can drive space weather intense enough to affect Earth's magnetic environment and upper atmosphere. Space weather is not weather in the ordinary sense of rain or clouds, but it can still disturb the systems around our planet. Bursts of solar activity can reshape magnetic conditions, energize particles, and alter the upper layers of air. It is a reminder that Earth is connected to the Sun in active and ongoing ways. Saturn's system includes dozens of moons, which means it behaves almost like a miniature solar system of its own. Each moon has its own size, composition, history, and orbit, creating a complex family around the giant planet. Instead of being a single, isolated world, Saturn is really the center of an entire system of icy and rocky companions. Looking at Saturn closely is a bit like looking at a smaller version of the solar system itself. Titan's atmosphere is so thick and hazy that it hides the moon's surface from ordinary visible light views. This dense orange haze makes Titan mysterious because its true landscape cannot be easily seen with normal observation. Beneath that blanket lie rivers, lakes, and landforms shaped by chemistry very different from Earth's. It is a moon that keeps much of its surface secret behind an atmospheric veil. Planetary ring particles around Saturn range from dust-sized grains to chunks large enough to resemble tiny moons. So the rings are not smooth bands at all. They are swarms of separate pieces, each orbiting Saturn under gravity. Some are as small as powder, while others are large enough to begin looking like worlds in their own right. The rings are beautiful because they are made of countless moving parts acting together. Enceladus is icy on the outside but is famous because evidence points to liquid water beneath its shell. That combination makes it especially intriguing because it suggests that a frozen surface does not always mean a frozen interior. Beneath a hard crust, heat and motion may still survive. It changes the way scientists think about where activity can exist in the solar system, especially on small icy moons. In the solar system, some of the strangest kinds of weather include methane rain, dry ice clouds, polar hexagons, and icy jets. Weather does not have to mean blue skies and water rain. On other worlds, entirely different substances can circulate through atmospheres and surfaces. The result is that familiar processes such as clouds, rain, and wind can happen in forms that feel almost completely new. Saturn's hexagon was first glimpsed in the 1980s and remained mysterious even after the Cassini mission studied it closely. That long period of observation matters because it shows the feature is not a brief storm or passing disturbance. It is a stable atmospheric pattern that has lasted for decades. The fact that it can persist so long makes it even more fascinating because giant planets are otherwise famous for constantly shifting weather. The Cassini spacecraft orbited Saturn from 2004 to 2017, turning the planet's ring system into one of the best-studied places beyond Earth. During those years, Cassini provided an enormous amount of detail about Saturn, its rings, and its moons. It transformed Saturn from a distant striped dot into a rich and changing world system. Much of what we calmly describe today was learned because that spacecraft stayed there for so long. Saturn is the farthest planet in the solar system that can usually be seen with the unaided human eye from Earth. That means people long before telescopes could look up and see a world nearly 1 billion miles away without realizing all that surrounded it. To the eye, it may look like a quiet point of light, but in truth, it is a ringed giant with many moons and complex weather. A tiny dot in the sky can hide an enormous system. Venus is sometimes called Earth's twin because its width is close to Earth's, even though its surface conditions are wildly different. From a distance, their similar size can make the comparison feel natural. But once scientists studied Venus more carefully, they found a world of crushing atmosphere, extreme heat, and a completely different surface reality. The nickname is useful, but it also shows how misleading appearances can be. Mars and Earth have similar day lengths, which is one reason Mars often feels oddly familiar in planetary comparisons. A Martian day is about 25 hours, which is close enough to Earth's daily rhythm that it feels almost relatable. This small resemblance helps Mars seem less alien than some other planets, even though nearly everything else about it is harsher and more extreme. Sometimes one familiar pattern is enough to make a distant world feel closer. Venus's thick cloud deck makes it look serene from space even though the world below is crushingly hot. Its pale surface of clouds can seem smooth and calm in images, almost gentle. But that visual softness hides one of the most hostile surfaces in the solar system. Venus is a perfect lesson in how outward beauty and inner severity can exist together in nature. A Venusian solar day and sidereal day are different because Venus rotates slowly while also moving along its orbit. A sidereal day measures one full turn relative to distant stars, while a solar day measures how long it takes for the sun to return to the same position in the sky. On Earth, those values are close, but on Venus, the difference becomes dramatic because of its slow and unusual rotation. It is one more way that even basic timekeeping changes from planet to planet. Venus's slow spin means weather and sunlight there do not follow an Earth-like daily rhythm at all. On Earth, daily heating and cooling shape the atmosphere in patterns we take for granted. On Venus, with such a drawn-out day, that familiar cycle is replaced by something far stranger. The movement of light, heat, and atmospheric behavior happens on timescales that would feel deeply unnatural to human experience. Jupiter rotates so quickly that one day there lasts only about 10 hours. For such a huge planet, that is astonishingly fast. This rapid spin helps shape Jupiter's broad cloud bands and contributes to its strongly flattened appearance at the poles. A giant world can move with surprising speed, reminding us that size and slowness do not always go together. Neptune completes a rotation in about 16 hours, much faster than Earth despite being far larger. Even far from the Sun, this distant giant keeps a brisk daily pace. Its quick spin influences its atmospheric patterns and helps shape the dynamic character of the planet. Though Neptune looks calm and blue in images, it is not a still world at all. Uranus rotates in roughly 17 hours, even though it is tilted so extremely that it appears to roll around the Sun. So Uranus combines two different oddities at once, a fairly quick rotation and a dramatic tilt, unlike that of the other major planets. This creates seasons and lighting conditions that are deeply unusual. It is one of the clearest examples of how a planet can break our expectations in more than one way. Mercury's rotation is so slow that one full turn lasts 408 hours. That means its spin is drawn out over an enormous stretch of time compared with Earth's quick daily cycle. A place like Mercury shows how varied the meaning of a day can be across the solar system. Time, in a planetary sense, is not a fixed human idea, but a property that changes from world to world. The Richat structure in Mauritania is so circular that astronauts have long used it as a landmark from orbit. From space, it looks almost like a giant eye set into the desert. Its shape is so striking and so easy to recognize that it stands out clearly against the surrounding land. Few geological features are large and symmetrical enough to become navigation markers for astronauts. Geologists interpret the Richat structure as an uplifted dome that erosion gradually peeled open layer by layer. So its circular rings were not built in one sudden event like a machine-made form. Instead, they emerged slowly as rock layers were lifted and then worn away over time. It is a beautiful example of how erosion can reveal hidden structure by removing material instead of adding it. Dust from the Sahara can travel across the Atlantic Ocean and show up as wide atmospheric haze seen even from space. Tiny particles lifted from desert ground can cross enormous distances through the atmosphere. This means one continent can influence skies, air quality, and even ecosystems far away. What seems local on the ground can become global once the atmosphere begins moving it. Aurora displays are powered by charged particles and magnetic interactions, not by reflected sunlight. They are not simply colored clouds or glowing mist. They are signs of energetic particles meeting Earth's atmosphere under the guidance of magnetic fields. This makes aurora light a visible expression of invisible forces, turning abstract physics into something people can actually see in the sky. Some of Earth's most dramatic electrical events happen far above the main storm cloud rather than inside it. That changes the way we imagine thunderstorms. A storm is not only what we see in the dark clouds and rain below, but also what unfolds high above it in thin air. The atmosphere has vertical depth, and storms can affect more of that depth than most people realize. Not all lightning is bright white upper atmosphere. Events include red and blue forms with very different shapes. These colors and forms depend on the air, altitude, and type of electrical discharge involved. So the sky can produce flashes that look nothing like the usual jagged lightning bolt. Nature often has more versions of a familiar process than first impressions suggest. The sky can create optical effects that look imaginary, but are well understood consequences of light passing through air, ice, and droplets. Green flashes, moonbows, glowing high clouds, and other rare sights can seem supernatural at first. But once explained, they often become even more interesting, because the mechanism itself is so elegant. Science does not remove the wonder. It often gives the wonder a clearer shape. Earth's atmosphere is layered enough that different parts of the sky can effectively be in day and night at the same moment. High clouds may still be lit while lower air and the ground have already darkened. Upper layers can glow even while ordinary weather below is fading. The sky is not one single flat space above us. It is a deep structure where light and darkness can coexist at different heights. Some natural patterns are memorable because they are geometric, like hexagons, circles, or canopy gaps. Human attention is naturally drawn to order, especially when it appears unexpectedly in nature. A six-sided storm, a ringed landform, or repeated gaps between tree crowns all feel striking because they combine beauty with structure. Geometry often makes a natural event feel instantly unforgettable. A map from orbit can show wind-blown dust, domed geology, and moving weather all in one view, turning Earth into a slow-motion abstract painting. From the ground, we experience rocks, storms, and air as separate things. But from above, their relationships become visible all at once. Dust plumes, cloud bands, and patterned landforms reveal that Earth is a connected system of motion, shape, and time. Some of Earth's strangest phenomena happen in deserts, some in the upper atmosphere, and some at the bottom of the ocean. They are spread across very different environments, yet all belong to the same planet. That contrast is part of what makes science so calming and so humbling. A single world can hold glowing skies, moving stones, hidden hot springs, and deep living darkness all at once. Some auroras happen so high above Earth that they are connected to particles escaping into space. That means an aurora is not only a beautiful curtain of light, but also part of a real exchange between our planet and the space around it. In the uppermost atmosphere, the air becomes extremely thin, and particles can gain enough energy to drift away from Earth's pull. So when we think of auroras, it helps to remember that they are not just decorations in the sky. They are signs that Earth's outer atmosphere is active, dynamic, and still interacting with the wider solar environment. The upper atmosphere is busy enough that it can glow, shift, and even lose particles into space. Near the ground, air feels steady and familiar, but high above us, the atmosphere behaves very differently. There, sunlight, charged particles, and magnetic forces can all influence the thin gases in ways that create light and motion. In simple terms, the top of Earth's atmosphere is less like a quiet ceiling and more like a constantly changing frontier. It is one of the reasons our planet is more open to space than it may first seem. A thunderstorm can influence layers of the atmosphere far above the altitude where aircraft usually fly. Most people think of storms as low or middle parts of the sky, with rain, wind, and lightning staying near the clouds themselves. But some storm-driven electrical effects rise much higher, reaching into parts of the atmosphere that feel far removed from ordinary weather. This means a thunderstorm is not only a ground-level event. It can be a tall, vertical system that connects the lower and upper sky in ways that are still being studied. Twilight clouds can look silver or electric blue because they sit so high in the atmosphere that they continue catching sunlight after sunset. Down below, evening has already turned the landscape dark, but those clouds remain illuminated because they are far above the shadow line. Their brightness can seem almost unreal, as if the sky is gently glowing by itself. In reality, it is a precise effect of height, angle, and sunlight. It is a calm reminder that sunset does not happen everywhere in the sky at the same time. Some atmospheric phenomena seem rare not because they are tiny, but because they are too brief, too faint, or simply happen in places where most people are not looking. A green flash lasts only a moment. A sprite may appear for an instant above a distant storm. Noctilucent clouds are easiest to see only during certain seasons and times of day. So rarity in nature often has more to do with timing and perspective than with impossibility. Many unusual sky events may happen more often than we imagine, but they pass quietly and quickly. Earth's atmosphere is layered enough that different parts of the sky can effectively be in day and night at the same moment. This sounds strange at first, but it makes sense when we remember that the sky is not a flat dome. It has depth. Higher layers remain exposed to sunlight longer, while lower layers fall into shadow earlier. This is why very high clouds can shine after sunset, and why certain atmospheric events appear to glow in darkness. The sky above us is really a stack of different zones, each experiencing light a little differently. Racetrack Playa in Death Valley became famous because stones there leave long trails behind them, as if they had moved by themselves across the desert floor. For many years, this looked deeply mysterious. The ground is flat, the environment is quiet, and some of the rocks are heavy enough that their movement seems unlikely. Yet long lines in the dried mud showed that motion really had happened. What makes the scene so striking is not speed or violence, but the opposite. The rocks seem to drift in a place that feels motionless. Some of the sailing stones in Death Valley weigh hundreds of pounds, which makes their movement feel even more surprising. If a pebble shifted in the wind, that would not seem too strange. But large stones leaving long tracks across a dry lake bed create a much stronger sense of mystery. The explanation turned out not to involve hidden forces, but a careful combination of water, thin ice, and wind. This makes the phenomenon even more satisfying. A heavy stone can move not because the desert breaks the rules, but because the rules work together in a quiet and unusual way. The motion of those sailing stones was linked to thin sheets of ice and wind rather than to anything supernatural. Under rare winter conditions, a shallow layer of water can freeze into thin floating panels around the stones. When morning sunlight weakens the ice and wind pushes the panels, the stones can slowly slide over the soft mud. The movement is gentle, not dramatic. It happens so slowly that people may never actually see it occur. That slow, quiet motion is part of what made the mystery last so long. Desert varnish is a dark coating that slowly develops on rock surfaces in arid regions. At first glance, it can make stones look polished or painted, as if someone carefully brushed a thin layer onto them. In reality, it forms over long periods through natural processes involving clay minerals, manganese, iron, and the effects of weather. The key thing to understand is that a desert rock is not always just bare rock. Time can place a skin on it, and in dry places that skin can remain for very long stretches of time. Desert pavements can look almost engineered, but they are natural surfaces shaped by slow sorting and weathering. In some dry landscapes, the ground becomes covered with closely packed stones that seem deliberately arranged. It can resemble a man-made road or stone floor. But this pattern comes from long-term natural processes as wind removes finer material and the surface gradually organizes itself. It is one more example of nature producing order without intention, simply by letting small changes add up over time. Lava tubes form when the outside of flowing lava cools and hardens while molten rock continues moving inside. This creates a kind of natural tunnel system. Imagine a river of fire developing a solid roof while the inside is still flowing. Eventually, the molten material drains away, leaving an empty passage behind. What is beautiful about lava tubes is that they preserve motion in reverse. After the lava is gone, the path remains, showing where liquid rock once traveled beneath a cooled shell. Those lava tubes can become cave-like passages that preserve the shape of one's moving molten rock. So a cave is not always made by water-dissolving stone. Sometimes it is made by fire. Inside a lava tube, the walls and ceilings may still show features from the original flow, like drips, ripples, or smooth, curved surfaces. That gives these places a very different feeling from other caves. They are like frozen pathways of ancient heat, turned quiet and hollow after the energy has passed. A blue hole is a water-filled sinkhole or cave system, but can appear from above as a dark circular patch in the sea. The deep blue or almost black color comes from the depth and the way light behaves in the water. From the air, a blue hole can look like a perfectly placed mark in the ocean, almost too cleanly shaped to be natural. But it is a geological feature, often connected to limestone landscapes and past changes in sea level. It is a good example of how water can hide vertical space in plain sight. Hydrothermal vents can release fluid hotter than 700 degrees Fahrenheit into the deep ocean. That temperature sounds impossible because we usually imagine water boiling away before becoming that hot. But at great depth, the pressure is so intense that water behaves differently. It can stay liquid even while becoming superheated. So on the dark sea floor, there can be jets of extremely hot fluid pouring into near-freezing seawater. The contrast is one of the strangest and most dramatic in the natural world. Hydrothermal vents form where seawater sinks into cracks in the ocean crust near regions of tectonic activity. As the water moves downward, it approaches hot rock heated by magma beneath the sea floor. The water warms, reacts chemically with the surrounding rock, and then rises again. Eventually, it emerges back into the ocean as mineral-rich fluid. In a simple sense, a hydrothermal vent is part of a giant natural plumbing system driven by Earth's internal heat. Deep-sea vent water can be superheated and still remain liquid because of the immense pressure at the bottom of the ocean. At the surface, water boils at a familiar temperature, but pressure changes those rules. In the deep sea, the weight of the ocean above keeps the water compressed, allowing it to stay liquid far past the boiling point we know from everyday life. This is one of those facts that feels almost impossible until pressure is considered. The ocean changes physics not by breaking laws, but by changing conditions. Earth has rock surfaces so polished by wind, water, or ice that they can look carved even when no human hand ever touched them. A smooth stone wall or rounded surface may seem shaped by design, but natural forces are capable of great refinement given enough time. Wind can sand surfaces. Flowing water can round and polish them. Ice can scrape and smooth them over long distances. The calm appearance of polished rock often hides the long patience of geological change. Some geologic structures look artificial because erosion reveals repeating bands, hexagons, rings, or domes. Human minds are especially sensitive to symmetry and pattern, so when we see a strong geometric form in nature, it can feel intentional. But many of these shapes come from the internal structure of rock and the way weathering exposes it. Erosion is not random destruction. Often, it acts more like a slow uncovering. It removes material and lets hidden forms become visible. A dry lakebed can still become active enough in rare conditions to move rocks across its surface. Most of the time, such places appear lifeless and still. Their cracked mud and open space seem fixed in place. But when just the right amount of water, cold, and wind arrives, the flat basin becomes a temporary stage for motion. This is a helpful reminder that a quiet landscape is not always inactive. Sometimes it is simply waiting for the rare conditions that allow change to appear. Desert landscapes preserve slow processes so well that a trail in mud can remain visible long after the motion that made it has ended. In wetter climates, marks are often erased quickly by rain, plant growth, or constant surface change. But dry environments can hold evidence for much longer. A sliding rock, a passing animal, or a brief flood may leave traces that last and stay readable. In that way, deserts often act like archives. They quietly store signs of motion in places that otherwise seem empty. Earth's crust can create both icy caves and volcanic tunnels, sometimes in the same broad region over geologic time. That is part of what makes the planet so varied. One set of processes can chill and preserve frozen underground spaces, while another can melt rock and carve fiery passages. These extremes do not cancel each other out. They simply show how many different paths geology can take. The same planet can produce structures shaped by freezing and structures shaped by molten heat. Some caves are not dissolved by water at all, but are built by fire in the form of cooled lava. This challenges the common idea that caves always form through dripping, dissolving, and erosion. Lava tubes show that underground space can arise from an entirely different process. Instead of rock being removed slowly by water, molten rock flows through and later leaves behind an empty shell. A cave, then, is not defined by one origin. It is simply a space, and Earth has many ways of making one. Windstorms and temperature swings can slowly build thin coatings on desert stones that make them look almost lacquered. The process is gradual, subtle, and easy to miss in the short term. But over long periods, mineral-rich films can accumulate on exposed surfaces, changing the appearance of the rocks. This is one reason old desert landscapes often feel visually rich, even when they seem barren. Time itself has been painting them, but very slowly and with a limited palette. From orbit, some landforms are so symmetrical that astronauts can recognize them almost immediately. The Richat structure is one example, but the larger lesson is that certain natural forms stand out even at planetary scale. Most landscapes blend into broader patterns when seen from far away, yet a few are so distinct in shape that they remain obvious from space. It is a fascinating idea that geology can create features large enough and clear enough to function as landmarks for people in orbit. Earth's strangest landscapes often look calm because the forces that shaped them worked very slowly. A polished rock wall, a circular dome, a desert pavement, or a blue hole may appear still and complete. But each one is the result of motion spread across immense spans of time. Water, wind, heat, pressure, and erosion all act patiently. This is one reason geology can feel so restful to think about. Its drama is often hidden inside slowness. Bioluminescence is so common in parts of the ocean that many animals, living hundreds of meters below the surface, can produce light. In the deep sea, sunlight fades away quickly, yet life still finds ways to make brightness. Instead of relying on the sun, these animals create light through internal chemical reactions. So darkness in the ocean is not always empty blackness. It can be a world of flashes, pulses, glows, and signals made by living bodies. Many ocean organisms use bioluminescence to warn predators, attract prey, or communicate with one another. Light in the ocean is not only beautiful, it is useful. A glow might lure something closer, scare something away, or help members of the same species find each other in darkness. In human experience, light usually helps us see our surroundings. In the deep sea, light often becomes part of survival itself. It is a tool, a language, and sometimes a trap. Fireflies are famous on land, but in the ocean, light-making species range from tiny bacteria all the way to sharks. That wide range shows how successful bioluminescence has been as a strategy in marine life. It is not limited to one branch of the tree of life. Very different organisms have found ways to use light for their own needs. This makes the ocean feel even more unusual, because one of its common patterns is something that seems extraordinary on land. Whale falls create sudden food bonanzas on the deep sea floor when the body of a whale sinks after death. In the open ocean, food reaching the deep bottom can be limited and scattered. But a whale carcass changes that all at once. It becomes an enormous package of energy and nutrients landing in a dark place where resources are often scarce. For deep-sea animals, it is not just a body. It is the arrival of a whole temporary ecosystem. A single whale fall can support a succession of different animal communities as the carcass breaks down over time. At first, large scavengers may strip away soft tissue. Later, smaller creatures and specialized organisms can feed on what remains, including material in and around the bones. So the whale fall changes not just the amount of life in one place, but the type of life there, over time. It behaves almost like a slow ecological story unfolding in stages. Scavengers may strip much of a whale's soft tissue in months, but the effects of the carcass can enrich nearby sediments for much longer. Even after the most visible parts are gone, the whale continues influencing the seafloor. Nutrients seep into the surrounding ground, and other organisms can benefit from what is left behind. This makes a whale fall more than a single feeding event. It becomes a long-lasting change to the local environment. Hydrothermal vent ecosystems do not depend on sunlight in the usual way, which makes them feel like separate worlds on the ocean floor. At the surface, most life is linked directly or indirectly to sunlight. But around vents, life can be supported by chemical energy from the Earth itself. This does not mean sunlight becomes irrelevant to the planet overall, but it shows that local ecosystems can run on very different foundations. It is one of the clearest examples of life adapting to deep and unusual conditions. Scientists have found flourishing animal life even beneath the seafloor around hydrothermal vent regions. That means the vent world is not limited to what sits openly on the bottom. Life can also exist in the cracks, spaces, and hidden habitats below the visible surface. This expands the idea of where ecosystems can exist. The deep sea floor is not just a boundary. In some places, it is also a roof over still more living space. Deep ocean animals can make their own light in darkness where sunlight never reaches. For humans, light usually comes from a lamp, a flame, or the sun. In the deep sea, light can come from the bodies of the creatures themselves. This ability gives the environment a quality that feels almost like a moving night sky. The darkness is real, but it is often punctuated by life-generated brightness that appears and disappears in brief moments. The pelagic zone is the open water part of the ocean, and it contains many of the most luminous animals on Earth. Unlike the seafloor, this is the vast water column itself, where creatures drift, swim, hunt, and hide in three-dimensional space. In that open darkness, light becomes especially useful. A flash or glow can help an animal stand out or disappear, depending on how it is used. The open ocean is therefore not only empty space, it is a huge living volume filled with subtle signals. Hydrothermal vents begin with ordinary seawater seeping downward through cracks in the crust. That simple beginning is part of what makes them so interesting. There is nothing exotic at the start, just seawater moving into rock. But once that water enters hotter and deeper regions, its journey changes dramatically. It heats up, reacts chemically, and returns transformed. So a vent is a reminder that extraordinary outcomes can begin with familiar materials following unfamiliar paths. After vent fluid is heated by magma, it rises again and can pour out as mineral-rich plumes into the ocean. As it emerges, it carries dissolved substances picked up from the hot rock below. When that fluid meets colder seawater, minerals can precipitate and build structures around the vent openings. In this way, the vent is not only releasing heat and chemistry, it is also helping shape the local seafloor. It creates both flow and form. A deep-sea environment can be both pitch black and chemically active at the same time. Darkness does not mean stillness. At hydrothermal vents and other deep habitats, there may be intense exchanges of heat, minerals, and biological activity even though no sunlight reaches the area. This combination makes the deep ocean especially fascinating. The absence of light does not reduce complexity. It simply changes the source of energy and the way that life organizes itself. Ocean bioluminescence is usually a chemical process rather than a reflection, which means the animals are truly generating light. This is very different from something merely shining because it catches outside illumination. In bioluminescent species, molecules react in ways that release visible light directly. So when a creature glows, it is not borrowing brightness. It is producing it. That makes ocean light shows feel even more remarkable because they come from chemistry happening inside living tissue. Some marine light displays happen when movement in the water disturbs tiny glowing organisms, making waves and wakes sparkle. In such cases, the ocean itself can seem to light up around a boat, a swimmer, or a moving current. But the glow is not coming from the water alone. It comes from countless tiny living things responding to disturbance. The effect is soft and brief, but it transforms motion into visible light, almost as if the sea were revealing every touch. Oh, the ocean hosts both giant carcass-based food islands and chemical vent-based ecosystems on its floor. These two systems are very different, yet both show how life gathers around concentrated sources of energy in otherwise difficult environments. A whale fall provides a sudden supply of organic material. A hydrothermal vent provides ongoing chemical energy and heat. In both cases, something localized transforms the surrounding darkness into a center of biological activity. Deep-sea bottom life is still less understood than life in the open ocean above it, even in the study of bioluminescence. Part of the reason is simple. The seafloor is harder to reach, harder to observe continuously, and far more hidden from ordinary human experience. Yet what has already been found there is rich and surprising. That means the unknown is likely not empty. It may simply be waiting in places that are difficult to study. A whale fall turns one large animal into habitat, food source, and ecological event all at once. It is not just that many organisms eat from it. The remains also create shelter, alter local chemistry, and influence nearby sediments. In that way, a single body becomes a temporary landscape. The death of one giant animal can reshape a small part of the deep sea floor for years, showing how matter in nature keeps changing form and function. The ocean can create hot springs on the seafloor while the surrounding water remains near freezing. This dramatic contrast is one of the reasons hydrothermal vents feel so strange. A creature can live in a place where cold, dark seawater sits right beside superheated, mineral-rich fluid. The temperature differences can be sharp and sudden over very short distances. So the seafloor is not always a uniform cold plain. In some places, it is a patchwork of extremes. The deep sea contains animals that use light, where land animals might use color. On land, bright feathers, fur patterns, or flower colors can matter in daylight. In the deep ocean, where sunlight is absent, produced light can take on some of those roles instead. It can attract, warn, display, or confuse. In this way, the deep ocean solves familiar biological problems with a different medium. What color does in sunlight, glow can do in darkness. Bioluminescence is much more common in the ocean than on land. That difference is important because it tells us something about environment and usefulness. In a dark ocean, making light can be extremely helpful. On land, where daylight is abundant and habitats are different, the same ability is less widespread. So the ocean did not just happen to produce glowing life. It offered conditions where light-making became especially valuable again and again. Deep ocean ecosystems can be fueled by falling bodies, chemical reactions, or drifting organic matter from the surface. This means the deep sea is supported by several different pathways of energy and food, not just one. Some resources arrive from above. Some are generated by geological activity below. And some come in sudden pulses, like a whale fall. That variety helps explain why deep-sea life can be so diverse, even in an environment that seems, at first glance, empty and uniform. Some deep-sea fish have tubular eyes that are specially shaped to detect the faintest traces of light from above. In the deep ocean, there is very little sunlight left, and most of it comes from higher waters, not from the sides or below. So instead of having eyes built for a wide, bright view, these fish have eyes designed like narrow, upward-looking tubes. That unusual shape helps them notice silhouettes, tiny flashes, or passing prey in a dark environment where almost every bit of light matters. Mirror-belly barrel-eye fish are known for their unusual, upward-looking eyes and their strange, delicate appearance. Their bodies seem almost unreal, as if they were designed for a world with very different rules from ours. In deep water, that is exactly the case. Their odd eye structure helps them look toward the dim light above, where food or danger may appear as shadows. They are a good example of how deep-sea animals often solve survival problems with body designs that look almost impossible at first glance. Larval glass squid can be so transparent that they look less like ordinary animals and more like pieces of drifting glass. This transparency is a practical advantage in open water, where there may be nowhere to hide. A nearly invisible body is a form of camouflage. Instead of blending into a rock or plant, the animal blends into the water itself. That can make it harder for predators to see, especially in an environment where clear shapes are easier to detect than faint outlines. Research vessels often discover that some of the ocean's strangest-looking animals are also very small. People sometimes expect the most unusual creatures to be giant, but the sea often surprises us by placing some of its most alien designs into tiny, fragile bodies. Small size can actually be useful in the ocean, especially for drifting organisms or larvae. What seems delicate to us may be perfectly suited to a world of currents, darkness, and constant movement. Open ocean eddies can gather unusual larvae and delicate young animals far from shore. An eddy is like a rotating patch of water that can trap and transport life within it. For tiny marine creatures, these moving water structures can act almost like floating neighborhoods. They bring together species that might otherwise be widely scattered. So the open ocean is not always evenly mixed. Sometimes it organizes living things into temporary communities shaped by water movement itself. Marine surveys often find creatures with transparent bodies because transparency is one of the most effective kinds of camouflage in open water. On land, animals may hide by matching bark, sand, or leaves. In the sea, especially away from the bottom, there may be no background at all except water and light. A transparent body helps reduce the visible outline of an animal. It is a simple but powerful solution to living in a place with very few hiding spots. The deep sea contains so much living light that darkness there is often broken again and again, rather than remaining completely black. When we imagine the deep ocean, we often picture unchanging darkness. But in reality, many organisms can produce flashes, glows, or pulses. That means darkness in the deep sea can be interrupted by life itself. It is a quieter kind of brightness than daylight, but it still turns the ocean into an active visual world. Even in an enormous ocean, a dead whale can briefly become the center of a whole local food web. That happens because a whale carcass contains a huge amount of stored energy and nutrients. When it sinks, scavengers arrive. Then other organisms follow in stages. In a place where food may be spread thinly over large distances, one whale can reshape the surrounding seafloor community. For a while, it becomes a small island of abundance in the dark. Hydrothermal vents show that life can gather around heat and chemistry instead of relying on sunlight in the usual way. That idea is one of the most surprising in all of biology. Near Earth's surface, life is so strongly tied to sunlight that it can be hard to imagine another basis for an ecosystem. But around vents, organisms can use chemical processes linked to hot mineral-rich fluids. This means life can thrive in places that seem completely cut off from the sun. Ocean depths support both sudden bursts of feeding activity and long, slow ecological successions. A whale fall can attract scavengers very quickly, while the later stages of decomposition and nutrient use may unfold over much longer periods. This mix of urgency and patience is common in deep environments. Some events happen in a rush, but their consequences last quietly for years. The deep sea is not a simple place. It contains both immediate drama and long-term change. Some of the most alien-looking animals on Earth do not live on another planet or in some unreachable cave. They live in ordinary seawater, just at depths humans rarely visit. This is part of what makes marine biology so humbling. The unfamiliar does not always require a distant world. Sometimes it exists right here on Earth, hidden only by darkness, pressure, and depth. The ocean contains forms of life that feel foreign, simply because our own experience is so shallow. Bioluminescence can be used defensively, offensively, or socially, depending on the species. One animal may glow to startle a predator. Another may use light to lure prey closer. Another may flash signals to find a mate or identify its own kind. The important point is that light in the ocean is not just decoration. It can play many roles, and different species use it in different ways based on what helps them survive. Chemical light in the sea can function as a lure, a warning, a disguise, or a signal. This makes bioluminescence one of the most flexible tools in the marine world. A glow might say, "Come closer, stay away, do not notice me," or "I am one of your own." The same basic ability, producing light, can be adapted to completely different purposes. That is part of why it appears so often in ocean life. A hydrothermal vent can begin with cold seawater and end with superheated fluid, making it one of Earth's strangest natural circulation systems. The water starts in a familiar state, but as it moves through cracks and encounters hot rock, it is transformed. It becomes hotter, chemically altered, and rich in dissolved minerals before rising again. This journey turns ordinary seawater into something that can help support unusual ecosystems on the ocean floor. Much of what falls from surface waters into the deep ocean becomes food for animals far below. Tiny particles, dead plankton, waste material, and the remains of larger organisms all drift downward. This slow rain of organic material helps feed life in places where sunlight never reaches. In other words, the deep sea is partly supported by leftovers from above. Surface life and deep life are connected, even when they seem far apart. The ocean floor can hold ecosystems that feel both ancient in style and newly discovered by science. Some deep-sea communities are built around processes that seem simple and old, like chemical energy and scavenging. Yet humans have only recently begun to study many of them in detail. This creates an unusual contrast. A system may have existed for a very long time, while human understanding of it is still new and incomplete. In some parts of the sea, nearly every passing wave, fish, or current can trigger flashes of living light. That means the water can respond visibly to motion. A disturbance does not just move through the environment. It can reveal itself by making organisms glow. The ocean then becomes almost like a hidden screen, showing the paths of movement and light. It is a beautiful example of life turning motion into a signal. A calm-looking ocean surface can hide ecosystems that are hotter than ovens and darker than caves. This contrast is one of the strangest truths about the sea. From above, the water may look flat, reflective, and peaceful. Deep below, however, there may be superheated vent fluid, unusual chemistry, and animals living in total darkness. The ocean often appears simple from the surface because it conceals its extremes so well. Some male red widow spiders repeatedly place themselves into the female's mouthparts until she eventually eats them. This sounds shocking, but it is part of a real reproductive strategy in some spiders. In such cases, mating and self-sacrifice become linked in ways that are difficult for humans to relate to emotionally. What matters biologically is not comfort or survival in our usual sense, but the transfer of genes. Nature sometimes produces strategies that feel harsh because they are focused so narrowly on reproduction. Not all black widow mating ends in cannibalism, despite the spider's famous reputation. Popular culture often turns animal behavior into a simple rule, but biology is usually more varied than that. Cannibalism can happen, but it is not guaranteed in every case. This is a useful reminder that well-known animal stories are often simplified. Real behavior depends on conditions, timing, and species-specific details, rather than on a single dramatic stereotype. Some bats can swim, using their wings and feet to move through water toward land. People usually think of bats only as flying animals, but their bodies can sometimes handle water better than expected. They are not built like fish or otters, of course, but if they end up in water, some species can paddle their way towards safety. It is one of those facts that widens our sense of what an animal can do beyond its most famous ability. Primates are unusual among mammals for how much they communicate with social groups through varied calls, gestures, and expressions. Their social lives are often complex, so communication becomes especially important. A look, sound, posture, or movement can help manage relationships, warn of danger, or coordinate behavior. This rich communication helps explain why primates often seem especially expressive to human observers. We recognize complexity in them partly because we are primates too. Primates move in many different ways, including climbing, brachiating, quadrupedal walking, and sometimes walking on two legs. That range of movement reflects the different habitats and lifestyles within the primate group. Some are built for tree branches. Others are more comfortable on the ground. Some swing using their arms, while others climb or leap. The variety reminds us that even within one branch of animals, there can be many different solutions to getting through the world. Some animal societies are so organized and coordinated that scientists compare them to miniature human systems. This does not mean they think like humans, but it does mean their group behavior can be surprisingly structured. Roles, signals, cooperation, and social rules can emerge in animal groups in ways that feel strikingly elaborate. Looking closely at social animals shows that complexity is not limited to human communities. Hummingbirds can enter torpor, a controlled low-energy state that sharply reduces body temperature and energy use. These birds live with extremely high energy demands, so torpor gives them a way to survive periods when food is limited or nighttime temperatures are low. In simple terms, they temporarily slow themselves down to save fuel. It is a remarkable adjustment for such a tiny, active animal, and it shows how survival sometimes depends on carefully lowering the pace of life. Torpor allows tiny birds with very fast metabolisms to get through cold nights without using up all their stored energy. A hummingbird burns energy quickly during the day, especially while hovering and feeding. At night, that fast-burning system could become risky if it stayed at full speed. By entering torpor, the bird reduces its needs until morning. It is a quiet physiological strategy that helps small bodies manage big energy problems. Some spiders use silk for much more than classic round webs. They also use it for drag lines, egg sacs, shelters, and courtship settings. Silk is therefore not just one tool. It is a whole material system with many uses. A spider may use it as a lifeline, a nursery, a home, or part of a mating display. This helps explain why silk has been so important in spider evolution. It is flexible, useful, and adaptable to many different needs. A spiderweb can act not only as a trap, but also as an information network, because vibrations tell the spider what has touched it. In that sense, the web functions a bit like an extended sensory surface. The spider may not see the prey clearly, but it can feel the pattern of movement through the silk. Different vibrations may suggest different kinds of insects, struggles, or disturbances. So the web is both a structure in the environment and a way of receiving information from it. Many bats rely on sound more than sight when navigating, making them masters of acoustic space. By emitting sounds and analyzing the returning echoes, they build a detailed sense of nearby objects. This allows them to fly through darkness, avoid obstacles, and locate food with impressive precision. Humans usually depend heavily on vision, so echolocation can feel almost magical. But it is simply another way of sensing the world, one built around sound rather than light. A flying fox is a bat that can have the face of a fox and the wingspan of a small child. The name fits because these bats often have fox-like facial features and can be surprisingly large. Their size can make them look dramatic in flight, especially compared with the smaller bats many people imagine first. Yet despite the impressive wingspan, they are still bats, showing just how much variety exists within that group of mammals. Some frogs are found by predators not only because they move, but because they make very specific sounds. A call that helps one frog attract a mate may also reveal its location to something hunting nearby. This creates an interesting tension in animal communication. The same signal can be useful and risky at the same time. In nature, many behaviors carry both benefits and costs, and survival often depends on balancing the two. Animal communication can include odor, touch, posture, color, song, vibration, and even electrical or chemical cues. Human communication focuses heavily on sound and sight, so it is easy to underestimate the range of other systems. But many animals live in worlds where smell, vibration, or body posture matters just as much as voice. Communication in nature is not one thing. It is a wide collection of methods shaped by each species' senses and environment. Some animal courtship displays are so symmetrical and carefully patterned that they look almost choreographed. The movements may involve repeated steps, strict timing, or highly consistent positions. To human eyes, such displays can seem like rehearsed performances. In biological terms, they are signals shaped by selection, where precision can matter because potential mates are judging quality, fitness, or species identity through the display. Social animals often spend a great deal of time managing relationships, not just finding food. Grooming, calling, resting near certain individuals, or responding to conflict can all be part of group life. This shows that survival in social species is not only about the physical environment. It is also about the social environment. Relationships can affect safety, access to resources, and reproductive opportunities, so maintaining them becomes part of daily life. Certain spiders can sacrifice themselves as a reproductive strategy, which is one of the stranger examples of biological investment. From a human perspective, the idea feels extreme. But in evolutionary terms, what matters is whether the act helps pass on genes. If self-sacrifice improves reproductive success under certain conditions, it can become part of the species' behavior. Nature often feels strange when it values successful reproduction more than individual survival. Even tiny animals can have highly specialized mating rituals that depend on exact timing and behavior. This reminds us that complexity is not limited to large brains or large bodies. A very small creature may still depend on specific movements, signals, or sequences during reproduction. Missing one step may mean failure. So even the smallest animals can live by precise biological rules that are invisible until closely studied. Some mammals can move through both air and water using the same basic limb structures, although not equally well in both. This is interesting because it shows how one body plan can serve more than one environment. A bat's wings are clearly specialized for flight, yet in some cases those limbs can still help the animal survive in water. Nature often works by modifying existing structures rather than inventing entirely new ones from scratch. Many primates are unusually hand-focused animals, and their dexterity shapes how they explore the world. Hands allow grasping, manipulation, careful inspection, and social behaviors like grooming. This fine control changes how primates interact with food, objects, and one another. In humans, this hand-centered way of engaging with the world becomes especially advanced, but its roots extend more broadly across the primate group. Animals do not all experience the same world because their senses emphasize different signals from the same environment. One species may live mainly through smell, another through sound, another through vibration or sight. So the same forest, cave, or ocean can feel completely different depending on who is perceiving it. This is one of the most calming ideas in biology. Reality is shared, but experience is not. Each species enters it through its own doors. Some animal groups survive mainly by lowering metabolism, while others survive by staying socially coordinated. These are very different strategies. One conserves energy inside the body. The other depends on interaction between many individuals. Yet both can be successful responses to environmental pressure. This shows that there is no single best way to endure challenge in nature. Different species solve the same problem through completely different styles of life. Spider silk begins as liquid protein, but becomes a remarkably strong fiber once it is spun. That transformation is one of the reasons silk is so fascinating. A substance starts inside the spider in one form, then becomes a thread with impressive mechanical properties outside the body. It is not just a sticky line. It is a carefully produced biological material that combines lightness, flexibility, and strength in a very effective way. Some bats roost in huge groups, turning caves and trees into temporary cities of hanging mammals. When many bats gather together, the scale can be surprising. The group becomes a living cluster of bodies, sounds, movement, and warmth. Roosting like this can offer protection, support social life, and help with temperature regulation. A bat colony may look chaotic from a distance, but it is often an organized and important part of the animal's daily cycle. The animal kingdom includes both creatures that glow and creatures that echolocate, showing that unusual abilities often arise in darkness. When light is limited, species need other ways to communicate, navigate, hunt, or hide. Some make their own light. Others build a picture of the world through sound. Darkness does not reduce possibility. In many cases, it encourages new forms of biological invention. Some predators listen for prey, some watch from above, and some chemically bait prey with light. These strategies show how varied hunting can be. A predator does not always chase fast or strike hard. Sometimes it waits, senses, or attracts. Hunting can depend on hearing, vision, chemistry, or deception. The method reflects the environment and the body of the animal using it. Predation in nature is as diverse as the prey it targets. Even when an animal looks fragile, like a larval glass squid, it may already be well adapted to a demanding environment. Delicacy and weakness are not the same thing. A transparent body, soft form, or tiny size may be exactly what helps the animal survive. In the ocean especially, what appears vulnerable to human eyes may actually be a successful design shaped by the realities of water, light, and predation. Mirabelli barreli fish show that an animal can solve the problem of darkness with optics instead of speed or strength. Rather than chasing through the dark with brute force, such fish rely on specialized eyes that gather the little light available. This is a good reminder that survival does not always come from power. Sometimes it comes from perception. Seeing well in a difficult environment can be just as important as swimming fast. Some marine larvae are so transparent that their internal structures become part of their camouflage. Instead of hiding the inside of the body, transparency makes even those internal features less obvious against the surrounding water. This kind of camouflage is very different from stripes or color matching on land. It works by reducing visibility altogether. The animal becomes hard to notice, not because it resembles something else, but because it barely seems to be there. Certain animal strategies seem almost opposite to one another. Hide by glowing, hide by being transparent, hide by remaining silent, or in rare cases, survive by being eaten at the right moment. These solutions sound contradictory, yet all can work depending on the species and environment. Nature does not follow one style. It tests many different paths. That is part of what makes the living world feel so endlessly inventive and quietly strange. Some forests show a phenomenon called crown shyness, where the tops of neighboring trees stop just short of touching each other. From below, this can create thin, winding gaps in the canopy that look almost like a carefully drawn network of lines. The effect can seem oddly polite, as if the trees are giving one another space. Scientists have explored several possible reasons for it, including the way branches respond to wind, growth, and light. Whatever the exact mix of causes, the result is strikingly orderly for something that emerges without planning. When crown shyness appears, the canopy can look as though the trees are quietly avoiding one another on purpose. That impression is part of what makes the phenomenon feel so gentle and unusual. Instead of forming one solid roof of leaves, the branches leave narrow spaces between crowns. Those spaces let light filter through in beautiful patterns. It is a reminder that even plant growth can produce shapes that seem almost social, even though no intention is involved. The Titan arum, often called the corpse flower, is famous for producing an odor that resembles rotting meat when it blooms. This smell is not accidental. It helps attract the kinds of insects that would normally be drawn to dead animals, such as carrion beetles and certain flies. For humans, the scent can be startling or unpleasant, but for the plant, it is an effective pollination strategy. It is one of the clearest examples of a plant using deception through smell, rather than through beauty or sweetness. The odor of a corpse flower is not always released as one smooth, steady wave. Instead, it can come in pulses. That means the plant's scent output changes over time during the bloom. This pulsing may help the smell spread more effectively or match the activity of pollinating insects. It also makes the event feel more active, almost as if the plant is deliberately broadcasting its signal in bursts. Even though it is rooted in place, the bloom can behave in ways that feel strangely dynamic. That rotten meat smell helps attract carrion beetles and other insects that normally investigate dead animals. The plant is using the insect's own instincts to complete its pollination process. Rather than offering nectar and floral sweetness, it imitates decay. This makes the corpse flower one of the more dramatic examples of plants solving reproductive problems through chemistry and mimicry. It is a strange but effective strategy, and one that shows how plants can manipulate animal behavior without moving from their place. The Titan arum produces the largest unbranched flowering inflorescence in the world. That means what looks like a single enormous flower is actually a giant flowering structure made up of many smaller flowers arranged together. It is botanically more complex than it first appears. The size of the structure is part of what makes it famous, because it transforms something as familiar as a bloom into something that feels almost architectural. A flower can become so large that it seems closer to a monument than a blossom. In cultivation, Titan arum can reach extraordinary heights, and in its native habitat, it can grow even taller. When people see one in a botanical garden, it often feels far larger than they expect a flower-like structure to be. Its height gives it a theatrical presence, especially when combined with its dark red interior and powerful smell. The plant does not simply bloom, it stages an event. That is one reason people gather to observe it when it finally opens. The giant underground corm of a Titan arum stores the energy needed for its rare and dramatic bloom. A corm is a swollen underground storage organ, and in this plant it can become extremely large. That stored energy is important because the bloom is such a demanding event. The plant may spend a long time gathering resources before producing its huge flowering structure. In simple terms, the show above ground depends on patience and storage below ground. Young sunflowers are known for heliotropism, which means they track the sun across the sky during growth. As the sun moves from east to west, the flower heads slowly shift to follow it. This motion is not random. It is linked to growth patterns and internal timing within the plant. For people watching over the course of a day, the movement may be too slow to notice easily. But over time, it reveals that some plants are more physically responsive than they first seem. Plant behavior can be rhythmic enough that scientists compare it to internal timekeeping systems. Plants do not have clocks the way humans build clocks, but they do have biological timing mechanisms that guide when certain actions happen. Leaves may open and close on schedule. Stems may orient with daily light patterns. Flowers may change position across the day. These rhythms help plants stay aligned with regular changes in the environment, especially light and darkness. Some forest canopies form natural mosaics where light enters through the exact spaces that neighboring crowns leave between each other. These patterns can make the ground below shimmer with patches of sun and shade. The effect may look artistic, but it comes from branch growth, leaf arrangement, and space between trees. It is one of those quiet examples where biological structure shapes light itself. The forest does not only block sunlight, it edits it. A corpse flower bloom looks like one giant flower, but botanically, it is an inflorescence made of many tiny flowers gathered into one large structure. This is important because it changes how we understand what we are seeing. The dramatic bloom is not a single floral unit enlarged to an extreme size. It is a coordinated cluster. Nature often creates giant forms by combining smaller, repeated parts, and the corpse flower is a very clear example of that principle. The inside of the Titan arum spathe is a deep crimson color, which helps strengthen the illusion of exposed flesh. This visual effect works together with the rotting odor to attract pollinators that are drawn to carrion. In other words, the plant is using both smell and appearance to complete the illusion. The combination is what makes the corpse flower so memorable. It is not only large, it is carefully convincing in a way that serves a specific biological purpose. Some plants attract pollinators with sweetness, while others use deception and imitate decay. That difference shows how varied plant strategies can be. One flower may reward visitors with nectar and a pleasant scent. Another may offer no reward at all, but trick insects into approaching by smelling like death. Plants do not all communicate with animals in the same emotional register. Some appeal to attraction, and some to confusion. Plant structures can become huge without being woody, which shows that great size in plants does not always require a tree trunk. The corpse flower is a good example. Its dramatic height does not come from forming a massive wooden body like an oak or cedar. Instead, it builds its size through a different kind of plant structure. This broadens our idea of how plants can become large. Strength and scale can come from more than one design. Crown shyness gives some forests a lace-like ceiling when viewed from below. The spaces between tree crowns create soft branching patterns overhead, almost like delicate stitching in the sky. This visual effect can make a forest feel especially calm and structured. The trees are not arranged for our benefit, of course, but the result can feel remarkably graceful. Natural growth often produces beauty as a side effect of function. Young sunflowers do not simply face east forever. During development, they can follow the sun across the day. That movement helps the plant make use of light in a dynamic way while it is still growing. Later, mature flowers often settle into a more fixed orientation. This shift from daily movement to steadier positioning shows that plant behavior can change over the course of development. Even within one species, the same plant may behave differently at different stages. A plant can spend years storing resources before producing a bloom that lasts only a short time. This is one of the more striking patterns in plant life. Long periods of quiet growth may lead to a brief dramatic event, like the flowering of a Titan arum. To humans, this can feel almost symbolic, but biologically, it is a strategy of timing and resource use. Plants often operate on schedules that are far slower and more patient than our own. One of the strangest things about plants is that many of their most dramatic actions are simply too slow for casual human observation. Because we move and notice things at human speed, we often think of plants as still. But if we could watch them on a time-lapse scale, many would seem much more active. They lean, open, twist, follow light, and change posture over time. Their stillness is often more about our perception than about their behavior. Forest crowns can interact in ways that resemble spacing rules, even though trees have no nervous system and no intention. Branches grow, sway, compete for light, and respond to repeated physical contact and environmental limits. Over time, this can produce the appearance of boundaries between neighboring trees. The result looks orderly, but it comes from local physical processes repeated again and again. It is another good example of pattern without planning. Some plants recruit insects by smelling like food, some by smelling like sex, and some by smelling like death. This wide range of strategies shows how flexible plant communication can be. Flowers are not only passive shapes waiting to be noticed. Many are active signal systems built to influence the behavior of animals. What seems beautiful or strange to us may simply be an effective message aimed at a specific kind of insect. The corpse flower blooms so rarely that botanical gardens often treat it like a major event. People gather, cameras appear, and updates are shared because the bloom does not happen often and does not last long. That rarity adds to the plant's mystique. It is not just unusual in form and smell. It is also unusual in timing. A long wait leads to a short-lived display, which makes the moment feel even more special to observers. What looks like stillness in a forest often hides growth strategies, daily timing, and competition for light. Trees do not walk or speak, but they are not passive in the biological sense. They stretch upward, spread outward, adjust leaf placement, and respond to their surroundings through growth. Much of plant activity is simply slow. Once that is understood, a forest begins to feel less like a frozen picture and more like a living process unfolding at a different speed. Some of the most dramatic plant signals are aimed not at humans, but at beetles, flies, and other pollinating animals. A scent that seems awful to us may be perfect for the intended visitor. A color or heat pattern we barely notice may be meaningful to an insect. This helps explain why some plants seem bizarre from a human point of view. They were never shaped to impress us. Their signals are part of conversations in another biological language. A plant's internal clock can influence how it positions leaves, stems, or flower heads through the day. This timing helps the plant match its actions to recurring conditions such as sunrise, heat, and darkness. In other words, plant behavior is not only shaped by immediate conditions, it is also shaped by rhythm. The ability to anticipate rather than merely react is one of the quieter but more impressive features of living systems. Giant flowers often achieve their size by combining many smaller floral units into one towering structure. This principle appears in several plant groups and helps explain how something can look singular while being built from repeated parts. Nature often reaches large scale through accumulation and arrangement, rather than by enlarging one piece alone. Once you notice this pattern, many plant structures begin to look more like biological architecture. The natural world includes trees that avoid touching and flowers that imitate carrion, both without conscious planning. These forms and behaviors can feel almost theatrical or intentional to us, but they arise from selection, growth, and interaction with the environment. That contrast is one of the calming things about biology. Complex outcomes do not always require a thinking designer in the moment. Sometimes the rules of life and environment are enough. Some plant traits feel almost theatrical because they evolved to manipulate animal behavior. A giant red bloom that smells like a carcass is not subtle. It is a strong signal, built to get attention from the right insects. Many flowers are less extreme, but the same logic applies. Plants often shape their form, smell, and timing around the sensory world of pollinators. What looks dramatic is often simply efficient. The plant kingdom solves practical problems with geometry, chemistry, timing, and patience rather than movement. A plant may use branching structure to capture light, scent molecules to attract insects, and internal rhythms to match the day. It does not need to run or chase to interact powerfully with the world around it. This is one reason plant life can seem so calm. It acts through slow design rather than quick motion. A forest canopy and a corpse flower both show that still organisms can create very dramatic visual effects. One shapes sunlight into a delicate ceiling of gaps and shadow. The other creates an enormous dark red bloom that draws crowds when it opens. Neither is moving through space, but both change the environment around them in strong ways. Stillness and impact are not opposites in biology. Human fingerprints are highly individual because of the fine ridge patterns on the skin of the fingers. These ridges form before birth and create textures that help with grip and touch sensitivity. The uniqueness of the patterns is why fingerprints have been so useful for identification. But beyond that practical use, they are also a good example of how the body carries tiny, detailed structures that we rarely think about in daily life. Goosebumps are a leftover mammalian reflex in which tiny muscles pull on hair follicles in response to cold or emotion. In furry animals, this reaction can make the coat stand up, helping with insulation or making the body appear larger. In humans, with much less body hair, the effect remains but is less useful in the same way. It is a small sign that the body still carries older patterns from deeper mammalian biology. Yawning is contagious enough that simply thinking about it, reading about it, or seeing someone else do it can make a person yawn too. This is one of those common experiences that still feels a little strange. A single action can spread through attention alone. The exact reasons behind contagious yawning are still studied, but the effect itself is easy for many people to notice. It shows how bodies and minds can respond to social cues in very subtle ways. Hiccups happen when the diaphragm contracts suddenly and involuntarily, followed by the rapid closing of the vocal cords. That quick closing is what produces the familiar hic sound. The event is small, but it reveals how finely coordinated breathing usually is. When that coordination is briefly interrupted, the result becomes very noticeable. Hiccups feel odd because they are so simple and so uncontrollable at the same time. The human body constantly uses electrical signals to move information through nerves. When you feel touch, move a muscle, react to heat, or notice pain, signals are being sent through networks of nerve cells. These signals are not like visible sparks, but they are real electrical changes moving through tissues. Much of everyday life depends on them. The body is quietly full of signaling events happening all the time without our awareness. Your sense of balance depends in part on fluid movement inside the inner ear. Small structures there detect motion and orientation, helping the brain understand whether you are turning, tilting, or standing upright. This is why spinning can make the world feel unstable. The fluid keeps moving for a little while, and the signals no longer match what your eyes and muscles report. Balance feels effortless most of the time, only because the system usually works in silence. Smell has an unusually direct connection to memory and emotion compared with many other senses. A scent can suddenly bring back a place, a person, or a feeling with surprising force. Part of that comes from how smell is connected in the brain to areas involved in emotion and memory. This makes scent feel intimate and powerful in ways that can be hard to explain. A smell can act like a shortcut into the past. Human skin is both a protective barrier and a sensory organ filled with receptors for pressure, temperature, and pain. We often think of skin mainly as an outer covering, but it is also a constantly active information surface. Through it, the body learns about heat, cold, texture, touch, and danger. So skin is not only what separates us from the outside world, it is also one of the main ways we stay in touch with it. Goosebumps can be triggered not only by cold, but also by music and strong emotion. This is part of what makes them so interesting. A response that likely began as a physical reflex tied to temperature can now also appear in moments of awe, fear, or beauty. The same tiny muscles respond in very different situations. It is a reminder that the body often uses old physical mechanisms in new emotional contexts. The brain can fill in missing visual information so smoothly that people rarely notice how much interpretation is involved in seeing. Vision feels immediate and complete, but it is not a simple camera recording. The brain is constantly assembling, predicting, and adjusting based on incomplete input. That is one reason visual illusions work so well. They reveal that seeing is an active process, not just passive reception. The human ear turns air vibrations into electrical signals, so hearing is both a mechanical and a neural event. Sound waves enter the ear, move structures inside it, and eventually become nerve signals that the brain can interpret. This makes hearing a layered process. Air movement becomes physical vibration, then biological signaling, then experience. A simple sound passing through the air becomes meaningful only after the body translates it. Eyes are always making tiny movements, and if they stopped moving completely, vision would actually begin to fade rather than improve. These small motions help keep the visual world active on the retina. Without them, the image could begin to disappear from conscious awareness. This is one of those strange facts that shows the body depends on motion even during activities that feel still. Steady seeing quietly relies on tiny, constant change. Taste is not only about the tongue, because smell contributes heavily to what people experience as flavor. When the sense of smell is reduced, food often seems dull, even if the tongue still detects sweet, salty, sour, bitter, and savory notes. This is why a blocked nose can change the whole experience of eating. Flavor is a combined sensory event, not a single one. Muscles can generate heat simply by working, which is why shivering helps warm the body. Shivering is not random trembling. It is a coordinated pattern of muscle activity that produces extra heat when the body is cold. The movement may feel uncomfortable, but it serves a practical purpose. It is one of the body's built-in ways of turning motion into warmth. Bones are living tissue that are constantly being remodeled rather than remaining fixed like dry sticks. Cells break down small amounts of bone and other cells build new bone in response. This ongoing process helps bones stay functional and adapt to changing demands. It also means the skeleton is more active than it appears. What seems like a rigid framework is actually a living system under constant maintenance. Human tears are not all the same because the body produces different kinds for lubrication, irritation, and emotional crying. Tears that keep the eye moist are different from tears caused by smoke, dust, or strong feeling. This makes crying more biologically varied than it may seem. What looks like one simple response actually includes multiple functions serving different needs of the eye and body. The body's circadian system helps coordinate sleepiness, hormone timing, and changes in alertness across the day. This internal timing system does not simply tell you when to sleep. It influences many body processes, helping align them with regular cycles of light and darkness. When circadian timing is disrupted, people often feel that many parts of life become less steady, not just sleep. The system acts like a quiet organizer inside the body. Skin can sense a gentle brush differently from a sharp poke because different receptor systems specialize in different forms of touch. That means the body is not receiving one simple signal called touch. Instead, it is sorting many kinds of contact into categories such as pressure, texture, warmth, pain, and movement. This fine sensory division helps explain why physical experience feels so rich, even when the skin is the only organ directly involved. The body uses involuntary routines like blinking, swallowing, and breathing adjustments without asking for conscious permission each time. These automatic actions free the mind from having to control every small survival task. Most of the time, they happen so smoothly that people barely notice them at all. Yet, if they stopped or became difficult, we would realize immediately how much life depends on this hidden background work. Human posture is an active balancing act rather than a passive state, because muscles are always making small corrections to keep the body upright. Standing still is not truly still on the inside. Tiny adjustments are happening continuously in response to gravity, movement, and shifting weight. This is why posture is better understood as ongoing control rather than frozen position. The body is quietly working even in moments of apparent rest. The brain can remap body sensation after injury or practice, which shows that the body you feel is not only a fixed physical object, but also a living map built inside the nervous system. In simple terms, the brain keeps updating how it understands the body. If a person trains a skill intensely, or if normal sensation changes because of injury, the brain can adjust how it interprets signals. This flexibility is one reason recovery, learning, and adaptation are possible. The body is real, but your experience of it is also something the brain is continuously shaping. A shiver is a patterned muscle response, not just random trembling. When the body gets cold, muscles begin making small, rapid contractions in a coordinated way. These contractions generate heat, helping warm the body from within. So, a shiver is actually a built-in heating strategy. It may feel messy or uncontrolled, but underneath it is a very practical system. The body is not simply reacting with panic to cold. It is doing organized work, Many people think silence means the total absence of sound, but the body itself often supplies its own quiet internal soundscape. Breathing, heartbeat, swallowing, blood flow, and faint muscular shifts can all produce small sensations or noises. Usually the brain filters much of this background information out. But in very quiet settings, people sometimes become more aware of it. Silence, then, is rarely complete. Often it is just the point where your own body becomes easier to notice. The human sense of time changes depending on attention, novelty, and emotion. A familiar hour may pass quickly, while a tense minute can feel unusually long. This happens because time is not experienced as a simple clock reading inside the mind. Instead, it is shaped by how the brain processes events, expectation, and memory. In everyday life, this means two equally long periods may feel very different. The clock can stay the same while lived time stretches or shrinks. Pain is not simply a direct readout of tissue damage, because the brain can amplify it or reduce it depending on context. This does not mean pain is imaginary. It means pain is an experience created by the nervous system using many kinds of information. Attention, fear, stress, memory, and circumstance can all influence how strongly pain is felt. The body sends signals, but the brain interprets them. That is why pain is both physical and perceptual at the same time. A yawn involves coordinated movements of the jaw, throat, chest, and facial muscles, rather than being one single, simple action. What feels like a brief automatic event is actually a sequence involving several body systems working together. Breathing changes, muscles stretch, and the mouth opens in a recognizable pattern. This complexity is part of why yawning feels so distinct. It is a small reminder that even ordinary reflex-like actions can involve surprisingly detailed coordination. Sweating cools the body through evaporation, which means heat can leave the skin as moisture turns into vapor. This is a very elegant system. Instead of carrying heat away with ice or cold water from the outside, the body uses a thin layer of moisture on the skin and lets physics do the work. When sweat evaporates, energy is removed from the surface, helping lower temperature. So sweating is not merely a sign of heat. It is part of the body's cooling technology. Your body quietly clacks the position of your limbs through a sense called proprioception, which tells you where parts of you are even with your eyes closed. Because of proprioception, you can touch your nose without looking or walk without staring at your feet every second. Sensors in muscles, joints, and tendons constantly send information to the brain about position and movement. This sense is so reliable that most people barely notice it, yet daily life depends on it almost all the time. Hearing your own recorded voice often sounds strange, partly because in everyday life you hear your voice through both air and the bones of your skull. When you speak, sound reaches your ears from outside, but vibrations also travel through your head internally. That combination makes your own voice sound richer or different to you than it does to others. A recording removes the internal pathway, so the result can feel unfamiliar even when it is accurate from the outside. Many ordinary body experiences feel automatic, only because the nervous system is performing constant hidden calculations. Balance, movement, breathing adjustments, eye coordination, and temperature regulation all depend on the brain and body processing information continuously. The work is real, but it happens below conscious awareness. In this way, normal life feels simple, not because it is simple, but because the body is extremely skilled at doing difficult things quietly. A whispering gallery can let sound travel along a curved wall in a way that surprises people standing far apart. In some spaces, a soft sound made near one side of a curved surface can be heard clearly on another side, even across a large room. This happens because the architecture guides the sound waves along the surface rather than letting them spread out normally. It feels almost magical, but it is a very real effect of shape, reflection, and acoustics. Aeolian sounds are tones made by wind, which means moving air can become a source of music without human hands touching an instrument. When wind passes over or through the right shapes, it can create vibrations that turn into audible tones. In this sense, the atmosphere itself becomes a performer. It is a beautiful example of how physical conditions can produce something that feels expressive, even when no living creature intends it. An Aeolian harp produces sound when wind moves across its strings, rather than when a person plucks them. The strings vibrate because of the movement of air, and those vibrations create soft, often haunting tones. What makes the instrument so unusual is that the player is not human. The player is the wind. So the music depends on weather, direction, and flow. It is a partnership between material and atmosphere. Resonance allows a small, repeated force to build a surprisingly strong vibration when the timing matches an object's natural frequency. This means something does not always need a huge push to move strongly. If the timing is just right, even a gentle, repeated influence can create a large effect. Resonance appears in many areas of physics, music, and engineering. It is one of those ideas that feels very powerful once understood, because it shows how timing can matter more than raw strength. A tuning fork can seem almost magical, because one struck fork may cause another matching fork nearby to vibrate through the air alone. What is really happening is that the sound waves from the first fork match the natural frequency of the second. Because the second fork is ready to vibrate at that same frequency, it begins responding. This is resonance in a very clean form. It makes invisible sound suddenly visible through motion. So bubbles show swirling colors because thin films of liquid interfere with light waves. As light reflects from different layers of the bubble's surface, the waves can strengthen or cancel one another depending on the film's thickness. That changing thickness creates shifting patterns of color across the bubble, so the colors are not painted onto it. They're built from light interacting with a very thin layer of liquid. It is a simple object containing elegant physics. Snow can muffle sound because its structure traps air and scatters acoustic energy. Fresh snow often contains many tiny spaces between ice crystals, and those spaces affect how sound moves. Instead of reflecting strongly and traveling far, sound may be absorbed or broken up. This is why snowy landscapes can seem unusually quiet. The world has not stopped making sound. The snow is simply changing how much of that sound reaches you clearly. Some sand dunes can sing, hum, or boom when dry grains move under the right conditions. This surprising effect happens when many grains slide together in a coordinated way, producing vibrations that add up into a low, audible sound. Not every dune can do this. The size, dryness, and shape of the grains matter. But when the conditions are right, a slope of sand can seem to produce its own voice. It is one more example of sound emerging from ordinary materials in unusual ways. Glass is treated in normal conditions as an amorphous solid, not as a liquid slowly flowing like syrup. People sometimes repeat the idea that old glass windows became uneven because glass is a liquid moving over centuries, but that explanation is misleading. Glass lacks the orderly crystal structure of many solids, which is why it is called amorphous. Yet in ordinary circumstances, it behaves as a solid. The strange appearance of old panes has more to do with how they were made than with flowing through time. Water can be supercooled below its normal freezing point if there is no suitable seed crystal or disturbance to start freezing. This means liquid water can remain unfrozen even when conditions seem cold enough for ice. but the state is delicate. A sudden shock or a tiny particle can trigger rapid freezing. Supercooling is a good example of how physical systems do not always change state exactly when we expect. Sometimes they wait for the right starting point. Ordinary ice is less dense than liquid water, which is why it floats. This single fact has enormous consequences. It means lakes and ponds usually freeze from the top down instead of from the bottom up. The ice forms a surface layer that can help insulate the liquid water below. If ice were denser than water, many aquatic environments would behave very differently in cold weather. A familiar winter sight, floating ice, depends on a very unusual property of water. A magnet can move a compass needle without touching it because magnetic interaction happens through a field. The field is not visible in the way a string or rod would be, but it has real physical effects. The compass needle responds by turning until it aligns with the magnetic influence around it. This is one reason magnetism feels so strange to people at first. Action happens across space without obvious contact, yet the outcome is consistent and measurable. Sound needs a medium such as air, water, or solid material, which is why empty space itself is silent to unaided ears. Sound is a vibration passed from particle to particle. If there are no particles close enough to carry that vibration along, the sound cannot travel in the usual way. This is why explosions in space do not boom the way they do in movies. The event may be violent, but without a medium between source and listener, no ordinary sound can pass. The pitch of a sound depends mainly on vibration frequency, while loudness depends more on amplitude. In simple terms, faster vibrations create higher notes, and stronger vibrations usually create louder sounds. These are different qualities, even though people experience them together. A sound can be high and soft, or low and loud. Separating pitch from loudness helps explain how rich and varied ordinary sound really is. Light can be bent, split, reflected, scattered, and interfered with, which is why the world can produce so many subtle visual effects. Rainbows, halos, green flashes, iridescent clouds, and bubble colors all depend on these different behaviors of light. What makes this calming to think about is that one thing, light, can create many experiences just by meeting different materials and angles. The world appears visually rich because light is flexible in how it behaves. A rainbow is not fixed at one place in the sky like a painted object. It depends on the observer's position relative to the light source and the water droplets. That means two people standing in different places are not seeing exactly the same rainbow, even if they think they are. The rainbow is a relationship, not a solid object hanging in one location. This makes it one of the most beautiful examples of how perception and physics work together. Moonlight is bright enough to produce a rainbow only because it is reflected sunlight. The moon is not generating its own visible glow in the way a star does. It is reflecting sunlight toward Earth. Under the right conditions, that reflected light can still bend and separate in droplets to make a moonbow. The result is fainter than a daytime rainbow, but the principle is the same. Night sometimes borrows enough light from day to create its own color. A wave can pass through water without carrying the same water particles all the way across the ocean. This is one reason waves are so interesting. When you watch the sea, it can look as though water itself is moving steadily forward in great sweeping lines. But often the energy is moving through the water while many individual water particles are mainly moving in smaller local paths. So a wave is less like a mass migration and more like a traveling pattern. Heat can move by conduction, convection, or radiation, which means the same kind of energy can travel through touch, fluid motion, or empty space. Conduction happens through direct contact. Convection happens when warm fluids move and carry heat with them. Radiation travels through electromagnetic waves, which is how the sun warms Earth across space. These three pathways explain many everyday experiences, from a warm metal spoon to rising hot air to sunlight on skin. Many physical illusions feel calming because they reveal order hiding inside ordinary materials. Bubble colors, resonance, snow-muted sound, singing dunes, and whispering galleries all arise from simple rules acting under the right conditions. Once understood, they do not become less beautiful. Instead, they become examples of how the world quietly organizes itself. Physics can feel restful when it shows that unusual effects are not chaos, but structure. Quipu were knotted string recording systems used in the Andes, often for accounting and administration. Instead of storing information in ink marks on flat pages, Quipu stored it in chords, knots, spacing, and arrangement. This shows that recording information does not require writing in the familiar alphabetic sense. Humans have found many ways to preserve knowledge, and Quipu are a striking example of a system where touch, pattern, and structure carry meaning. A record can exist without ink if information is stored in position, pattern, color, or physical arrangement instead of handwriting. Quipu help make this idea easier to understand. We often assume information must appear as written symbols, but that is only one method. A system can still be formal and useful even when it is built from chords and knots. This widens our sense of what a document or record can be. Writing was independently invented in only a few places in the ancient world. That makes writing one of the most important and also one of the rarest major human inventions in terms of separate origins. Many societies used writing after learning from earlier traditions, but only a limited number appear to have developed it on their own. This fact helps show how significant it was when humans first discovered stable ways to record language and information visually. The Maya developed one of the most visually varied writing systems ever created, combining pictorial forms with signs that represented sounds and meanings. Their script was not a simple alphabet in the modern sense. It was richly structured and visually expressive at the same time. This made it both a writing system and a form of design. Looking at Maya writing reminds us that written language can be artistic as well as functional. Maya writing appeared on stone, ceramics, shell, wood, hides, textiles, and folded books. This wide range of surfaces shows that writing was not limited to a single material. Information could be carved, painted, or inscribed, depending on the object and the purpose. In this way, a culture's record-keeping system becomes visible across daily life, ceremony, and architecture. Writing can live on walls, vessels, and fabric, not just on pages. Ancient records were not limited to paper-like materials because buildings themselves could serve as historical texts. A monument or temple could preserve names, events, power, and memory directly in its structure and decoration. This means that in some cultures, history was not stored separately from the built environment. You could read the past not only in books, but in the very surfaces of important places. Dynastic history in Maya culture was sometimes recorded in architecture itself. A building might carry carved texts and images that linked rulers, events, and identity to a physical location. That makes architecture more than shelter or display. It becomes a memory system made of stone. In such cases, a city is also a record. Walking through it means moving through preserved political and historical meaning. A knot can function as data when it is part of a formal recording system rather than just a random tangle. This is one reason Quipu are so fascinating. They show that information can be encoded physically in shape and arrangement. A knot stops being merely a knot once it belongs to a system that gives it meaning. In human culture, matter becomes information when structure is interpreted consistently. Human societies have stored information in strings: stone, clay, bark, bone, cloth, and carved monuments. This variety reminds us that information technology did not begin with paper or computers. People have long used whatever materials were durable, available, and meaningful in their environment. The urge to preserve memory and organize knowledge is very old. The materials change, but the goal remains familiar. Writing systems do not all look like alphabets. Some combine symbols representing sounds, words, ideas, or several of these at once. This is important because modern readers often assume writing naturally works one way. But human cultures have invented many different visual systems for language. Some are compact, some decorative, some highly phonetic, and some mixed. The history of writing is therefore not one straight line, but many parallel experiments in communication. One reason ancient scripts feel mysterious is that the surface they are written on may survive long after the language around them has vanished. The symbols remain, but the people who read them, spoke them, and explained them are gone. This creates a quiet puzzle for later generations. The material record survives, while the living context fades. Decipherment is often the effort to reconnect those two things. The history of communication includes systems that are read by AIs, by fingers, and sometimes by counting or tracing structure. Quipu especially remind us that meaning does not always have to live in visible text alone. Information can be tactile and spatial. This broad view of communication makes human creativity feel larger. We do not only write, we arrange, knot, carve, and pattern meaning into the physical world. A city can preserve memory in walls and monuments just as a library preserves memory in books. Streets, buildings, carvings, and plazas, they all carry traces of the people who made them and the stories they meant to preserve. In this sense, place itself becomes a record. Memory does not always sit on a shelf. Sometimes it is built into stone and lived space. Ancient record-keeping was often more physical and spatial than modern people expect. We are used to pages, screens, and linear lines of text. Earlier systems often depended much more on objects, location, material arrangement, and bodily interaction. This does not make them primitive. It simply makes them different. Information has always had form, and not all forms resemble a book. Some of humanity's oldest information technologies are surprisingly tactile. Knotted cords, carved surfaces, and shaped objects all require the hand as well as the eye. This gives record-keeping a physical dimension that can feel very direct. Information is not floating abstractly. It is built into matter. That is a useful thing to remember even today, when so much information seems weightless and invisible. A document does not need letters to be systematic. It only needs a reliable structure that can carry and preserve meaning. This is what makes alternative record systems so important. They show that writing-like functions can exist without looking like modern writing. Humans are flexible in how they turn pattern into knowledge. The form may vary, but the principle of organized meaning remains. The look of a script can reveal that writing is also a design problem, not only a language problem. A writing system must be readable, repeatable, and suited to the materials used for making it. This means shape matters, arrangement matters, visual style matters. Even when the goal is practical communication, writing still lives in form. The history of script is therefore partly a history of visual invention. Ancient American civilizations developed formal systems for recording history long before European contact. This is important because it corrects the false idea that complex historical record-keeping belonged only to a few Old World traditions. Many societies in the Americas created sophisticated ways of preserving memory, identity, and administration. Their systems deserve to be seen as real information technologies in their own right. Information can survive because of durable material, because it is copied repeatedly, or because it is built redundantly into culture. A text on stone lasts for one reason. A story retold across generations lasts for another. A record reproduced many times lasts for still another. What survives from the past depends not only on what was created, but on how it was preserved and carried forward. The story of writing is less the story of one invention spreading everywhere, and more the story of several separate human solutions to the same problem. People in different places faced similar needs: to count, remember, mark identity, store history, and coordinate society. The answers they created did not always look the same. That diversity is one of the most beautiful parts of human cultural history. Many paths led toward memory made visible. One of the oddest things about time is that a day can mean more than one thing. It can mean one full rotation of a planet relative to distant stars, or it can mean the time it takes for the sun to return to the same place in that planet's sky. On Earth, those two measurements are close enough that most people never think about the difference. But on other worlds, especially slow or strangely rotating ones, the difference can become huge. It is a quiet reminder that even the simple word day is not as simple as it first seems. Planetary calendars would feel deeply unfamiliar to human beings because even basic words like day, month, and year stop behaving in the ways we expect. On Earth, our time system feels natural because it matches the rhythms we live inside. But on a planet where the sun rises slowly, or where a year ends before a day does, daily life would feel very different. Time would still be real, but it would no longer move in the comfortable pattern our bodies know. That makes the solar system feel not only physically diverse, but temporally diverse too. A view of Earth from orbit can reveal dust drifting across oceans, giant weather systems moving over continents, and broad geological structures spread across the land. From that distance, the planet can look like a huge, slow painting made of air, water, and rock. What feels separate from the ground becomes connected from above. Clouds become patterns, deserts become sources of haze, and landforms become visible shapes. It is a gentle way of seeing that Earth is one large, moving system. The same planet that creates moonbows and red sprites also creates stone trails across dry desert lake beds. That contrast is part of what makes Earth so interesting. A single world can have strange lights high above thunderstorms and slow-moving rocks on cracked mud far below. These things seem unrelated at first, yet they are all part of the same physical planet. Earth is full of quiet extremes, and many of them sit far outside what most people notice in daily life. Some of Earth's strangest phenomena happen in deserts, some in the upper atmosphere, and some at the bottom of the ocean. They belong to very different environments, yet they all remind us of the same thing. Nature does not become less surprising just because we live inside it. Whether it is high above us, deep below us, or spread out across distant land, the world keeps producing patterns and events that feel unusual once we pause long enough to notice them. The natural world often repeats one calming pattern across many scales. Invisible forces leave visible traces. Wind leaves dunes and varnish. Water leaves polish, caves, and wave patterns. Magnetic forces move compass needles. Light leaves color in bubbles and rainbows. In many cases, the force itself cannot be seen directly, but its effect can. That makes science feel a little like reading handwriting left by things that never speak out loud. Light can reveal structure in rings, clouds, bubbles, and thin films by making pattern visible where plain matter might otherwise seem simple. a bubble becomes full of moving color. Saturn's rings become bands of brightness and shadow. High clouds glow after sunset because of where they sit in the atmosphere. Light does not only allow us to see objects, it often helps us see relationships, layers, and form. Some of the most peaceful-looking natural scenes exist because of powerful forces acting very slowly over long periods of time. A smooth rock surface may have been shaped by ice. A perfect circular landform may have been revealed by erosion. A quiet desert floor may preserve evidence of rare motion and weather. Calmness in nature often sits on top of very long histories of change. What looks still in the present may be the result of great patience from the past. Transparency is a major survival strategy in open water because being hard to see can matter more than being armored. In the ocean, especially away from the seafloor or reefs, there may be nowhere solid to hide. A body that becomes nearly invisible gains protection in a different way. This is why so many marine larvae and delicate small animals look glass-like. The safest shape in a clear world is sometimes one that almost disappears. Sound can curve, light can bend, and rock can move, but only under very specific physical conditions. That is part of what makes rare natural events feel so memorable. They are not random miracles. They are precise outcomes waiting for the right situation. A whisper follows a curved wall. A rainbow appears at a certain angle. A stone slides when water, ice, and wind align. The world can be surprising without ever becoming lawless. Some of the strangest organisms on Earth do not hide in legendary places. They drift in seawater, often far from shore and far below the surface. This is a quiet but powerful thought. The extraordinary is not always locked away in some impossible location. Sometimes it exists in familiar substance, water, only at depths and conditions we rarely visit. A large part of the planet's mystery is simply hidden by access, not by distance. A landscape can look empty while still holding evidence of past water, old ice, wind-driven change, or ancient fire. Deserts especially can seem bare at first glance, but careful observation often shows trails, coatings, polished rock, layered surfaces, and preserved marks of motion. What looks empty is often just slow. The land has not stopped speaking. It is simply speaking in forms that ask for more patience. A storm is not only a weather event near the ground. It can also be an electrical event extending high into the atmosphere above. Once we understand sprites, jets, and other upper atmosphere effects, thunderstorms feel taller and more layered than they first appear. Rain, lightning, and wind may be the part we know best, but the storm can continue upward into thin air in forms that are harder to see and easier to miss. A forest canopy and a planetary ring both display large patterns that emerge from many smaller interactions. In one case, countless leaves, branches, and growth decisions create a textured ceiling of light and shade. In the other, countless particles orbit together to form bright, sweeping bands around a planet. The scales are wildly different, yet the principle feels similar. Order often arises from many small parts following simple rules together. Biological oddities often seem intentional, but many are simply the result of evolution solving narrow, practical problems over long stretches of time. A flower that smells like decay, a fish with upward-pointing eyes, or a spider with extreme mating behavior can feel almost designed for storytelling. But each trait exists because it helped in some way under certain conditions. Nature often looks dramatic, not because it aims for drama, but because function can take surprising forms. Deep-sea life shows that darkness does not reduce variety. It simply changes the rules under which life operates. In the absence of sunlight, vision changes, food sources change, and communication changes. Yet the result is not emptiness. It is a different type of richness. The deep sea contains light-making animals, chemical ecosystems, transparent bodies, and unusual senses, all because life continued adapting even when sunlight disappeared. The difference between eerie and beautiful in nature is often just context, not mechanism. A corpse flower can feel unsettling because of its smell, but its biology is elegant. A moonbow can feel gentle because of the darkness around it, though it forms by the same basic physics as a rainbow in daylight. The same process can feel haunting or peaceful depending on where and when we encounter it. Understanding often softens the strangeness without removing it. Things that seem supernatural often become more interesting, not less, once the mechanism is understood. Moving stones, glowing clouds, blooming dunes, and light-producing animals all sound mysterious at first. But when science explains them, the explanation usually adds depth rather than taking wonder away. Instead of simply saying it happens, science lets us see why it happens. And in many cases, the why is every bit as beautiful as the event itself. The upper atmosphere, the desert floor, and the ocean trench all produce phenomena that people once described mostly as mysteries. That is not because these places break the rules. It is because they are difficult to observe directly and often act outside ordinary human experience. Once careful observation reaches them, the mystery becomes clearer without disappearing entirely. The world remains strange, but the strangeness becomes readable. Some natural patterns stay in memory because they are geometric. Hexagons, circles, canopy gaps, and ringed structures speak strongly to the human mind because we notice order quickly. A six-sided cloud system or a giant circular landform feels unforgettable, partly because it seems too structured to be accidental. Geometry gives certain natural events a kind of visual authority. It makes them feel precise, even before we know what caused them. Other patterns remain memorable because they are brief rather than geometric. Twilight clouds fade. Sprites flash. Odors pulse from a bloom and then disappear. Part of their power comes from their timing. They do not stay long enough to become ordinary. They pass, and because they pass, they feel more delicate. Short-lived natural events often stay in memory for the same reason quiet music does. They arrive gently and leave before we fully settle into them. Many things humans call quiet are not truly inactive. They are systems with constant low-level motion that simply unfold too slowly, too softly, or too subtly for us to notice right away. Forests grow, bones remodel, clouds shift, rings orbit, and deserts preserve tiny changes over time. Much of the world is active without being loud. Once that becomes familiar, stillness begins to feel less empty and more alive. The Earth system links rock, air, water, and life so closely that one phenomenon often depends on more than one of them at the same time. Hydrothermal vents depend on geology and ocean water. Noctilucent clouds depend on atmospheric conditions and sunlight. Whale falls affect biology and sediment. Many natural facts become clearer when we stop thinking in isolated categories. The planet works by connection more often than separation. Information can be carried by knots, odors, vibrations, colors, electrical pulses, or orbital timing, depending on the system involved. A kripu stores information physically. A flower sends a message through scent. A spider reads vibrations in silk. A nervous system uses electrical activity. A planet measures time through motion. Meaning is not restricted to words. Across nature and culture, structure itself often becomes a way of carrying information. Strange facts often become relaxing facts when they reveal reliable patterns instead of random chaos. A thing may sound impossible at first, but when it turns out to follow steady rules, it often becomes less unsettling and more satisfying. That is one of the softer gifts of science. It does not flatten the world into dullness. It shows that unusual things still belong to a larger order. One reason nature feels endless is that each environment seems to invent its own solutions to light, heat, motion, and communication. The deep ocean uses bioluminescence. Forests shape light with leaves. Deserts preserve slow traces. The upper atmosphere glows under charged particles. Again and again, a problem appears, and a different answer forms around it. The variety itself becomes part of the beauty. Some solutions in nature involve making light, some involve avoiding touch, and some involve imitating decay. These approaches sound completely different, yet each one arises because it works in a specific context. A glowing animal, a tree crown leaving space, and a corpse fur tricking insects all show that success in nature does not look one way. The world solves its problems through many styles, from subtle to dramatic. The same scientific world contains both the precision of planetary timing and the messy richness of a whale fall, and both follow real rules. One speaks in orbits, rotations, and exact measurement. The other unfolds through decomposition, feeding, and ecological succession. Yet neither is outside nature's order. This contrast is soothing because it shows that precision and complexity can belong to the same universe without contradiction. Many beautiful phenomena are side effects rather than direct goals. Iridescent clouds, soap bubble colors, sunlight in rings, and glow in disturbed water often arise because of physical structure, not because beauty itself is being aimed at. Yet beauty still appears. That is one of the gentlest ideas in science. Grace often arrives as a consequence, not a command. A phenomenon does not need to be rare everywhere to feel rare to a person. It may simply be rare to witness from one place at one moment. Sprites may happen beyond the horizon. A green flash may vanish in seconds. A moonbow may need darkness, moisture, and the right angle all at once. Many wonders are ordinary in the larger world and still feel precious in a human life because of timing. When people call something strange, they often mean that it is real, but outside ordinary daily experience. That is a useful way to think about the word. Strange does not have to mean impossible, frightening, or unnatural. It can simply mean not often noticed. In that sense, much of science is an education in widening what feels familiar. A dead whale, a blooming Titan arum, and a sprite above a thunderstorm all show that brief events can still matter deeply in ecology or science. Some things are important not because they last long, but because of the role they play while they are here. A bloom may draw pollinators and attention. A whale fall may feed whole communities. A brief atmospheric event may reveal hidden physics. Short duration does not mean small significance. Some of the most remarkable facts on Earth depend on scale. They are too large to feel directly, too slow to notice in real time, too high to watch easily, or too deep to visit often. That is one reason the world can seem ordinary and extraordinary at once. Many wonders are present, but they unfold outside the narrow band of scale where human attention works best. Calmness in science often comes from realizing that even bizarre things usually happen for repeatable reasons. Moving rocks, glowing seas, and rotating worlds are not random acts of confusion. They arise from material, energy, timing, and structure. Once those relationships become visible, the world feels less like a pile of unrelated oddities and more like one connected field of causes quietly expressing themselves. Nature repeatedly turns ordinary ingredients like water, carbon dioxide, stone, protein, and air into extraordinary results. Water becomes clouds, ice, waves, and hydrothermal systems. Carbon dioxide becomes dry ice clouds on Mars. Protein becomes spider silk. Air becomes sound, wind music, and optical effects. The ingredients are familiar. The outcomes are what surprise us. The world is often most creative with the most common materials. You can learn a great deal about a system by looking at what it leaves behind. A stone trail reveals movement. A canopy gap reveals growth patterns. A knot pattern reveals stored information. A mineral deposit reveals fluid flow. Often the direct event is over, but the trace remains. Science frequently works by reading these traces carefully and learning how to reconstruct the quiet history behind them. Some of the best evidence in science is indirect. A cloud's color may suggest its composition. A line in the mud may reveal a moving stone. A chemical trace may point to heat below the sea floor. Direct observation is powerful, but the world often tells its story through effects instead of explanations. Learning to trust careful traces is part of learning how science listens. The natural world is full of things that look designed for storytelling, even though no one designed them for that purpose. A hexagon at a planet's pole, a flower that imitates decay, a fish that sees upward through darkness, a dune that sings. All of these feel almost literary, yet they are simply outcomes of physics and biology. Reality often arranges itself in ways that resemble fiction without needing fiction to make them real. One continuity across nature is that certain patterns repeat again and again, branching, spiraling, pulsing, drifting, clustering. These patterns show up in plants, fluids, clouds, ecosystems, and planetary systems. The repetition is comforting because it makes the world feel related to itself. Different things are not always disconnected. Sometimes they are variations on older shapes. Another continuity is that hidden layers matter. There may be liquid under ice, roots under soil, a corm under a flower, thin air above a storm, or hot circulation beneath the seafloor. Surfaces tell part of the story, but often not the deepest part. Science becomes gentler when it teaches us to expect depth beneath appearance, not as a threat, but as a normal feature of the world. Many of the most interesting facts arise in boundary zones where two conditions meet. Light and darkness, hot and cold, ocean and crust, air and storm, life and death. These edges often produce special behaviors and structures. Boundaries are where differences touch, and that touching often creates motion, exchange, and visible form. Much of the world's quiet beauty lives at thresholds. The world often stores information physically, in layers, haze, tracks, structures, and repeated form. A ring around Saturn preserves orbital history. A desert surface preserves movement. A quipu preserves records through knots. Physical things remember. They may not remember in words, but they still hold traces of what has happened. In that sense, matter itself can become a kind of memory. What makes a fact relaxing is often not the topic itself, but the clarity of the pattern behind it. A strange biological adaptation or unusual geological event may sound sharp at first, but once it is understood, the mind can rest inside the explanation. Pattern is calming. It gives the unfamiliar a place to belong. Seen together, strange facts suggest that Earth and the wider solar system are not chaotic collections of exceptions. They are structured places capable of unusual outcomes. The hexagon on Saturn, the clouds on Mars, the vents on the seafloor, the signals in the body, the records in knots, all of them fit within knowable systems. The world is not less mysterious for being structured. It is more beautifully mysterious because of it. A person can stand on one planet, look toward another in the sky, and still be surrounded by phenomena as strange as anything imagined on that distant world. Moonbows, singing dunes, glowing seas, moving stones, and hidden caves all belong to the same earth beneath our feet. Distance is not always what separates us from wonder. Often what separates us is attention. Some of the best reminders of nature's creativity come from places where familiar categories blur. A cave can be made by lava rather than water. A rainbow can appear by moonlight rather than sunlight. A flower can smell like decay. A day can last longer than a year. These moments soften the borders of ordinary thinking and invite a gentler kind of curiosity. Scientific understanding often begins with someone noticing that an apparently impossible thing keeps happening. A rock seems to move. A dune seems to sing. A cloud glows in darkness. At first, the event may feel like an exception, but repeated attention turns surprise into a question, and the question into study. That process, noticing patiently, is one of the quiet foundations of science. The more carefully people observe the world, the less ordinary life begins to look. Familiar things develop edges, details, and hidden processes. Wind becomes sound. Skin becomes a sensing field. Water becomes a strange substance with unusual behaviors. The goal is not to make the world unsettling. It is to make it richer. Careful attention often reveals that wonder was present long before we named it. Strange facts become especially memorable when they connect the familiar to the unfamiliar. Wind making music, trees leaving graceful gaps, light appearing in living bodies. All of these start with something known and then take one step beyond it. That step is often enough to widen the mind. Science does not always need the farthest galaxy to create wonder. Sometimes it only needs a familiar thing behaving in an unfamiliar way. A gentle way to think about the natural world is this. Calm surfaces often hide intricate systems, and those systems are frequently stranger, softer, and more beautiful than the surfaces first suggest. Under the stillness, there is pattern. Under the pattern, there is relation. And under all of it, the world continues quietly turning, glowing, drifting, growing, and remembering in its own patient way.